Welcome, video example 13, Unit 2, Chemistry 1B. Okay, this is a slightly more challenging problem where we're asked to calculate K, but here we're given delta H and delta S. Okay, so here we have the Haber process again at 500 degrees C. Remember that we had to convert to Kelvin, so this becomes 773 Kelvin. And we're given the delta H and the delta S values. Okay, so we also need to assume that delta H and delta S do not change with temperature in order to do this problem. And then they end up with this funny equation here, and you say to me, Prof, where did this thing come from? Well, remember, delta G is equal to minus RT ln K. But we're given delta H and delta S, so therefore we need to use the Gibbs equation, which says delta H minus T delta S is equal to minus RT ln K. Okay, so then in order to get ln K, I divide both sides by minus RT. So it becomes delta H minus over RT is equal to, minus T delta S, the T cancels. Let me just write it in so that you can see what I'm doing. T delta S over RT is equal to ln K. The temperature cancels here, so I end up with ln K is equal to delta S over R. That becomes a positive because I've divided by a negative here, So that becomes delta S over R, so it's minus delta H over RT plus delta S over R. Okay, so that's where this equation comes from, is the derivation I've just done over here. Okay, so now we can plug our values in, making sure that we have the right units all the way through. Remember, when in doubt, convert the kilojoules to joules, which we'll need to do. So the 92.38 kilojoules becomes 92,380 joules. Okay, so that's that value here. We have the gas constant, we have the temperature in Kelvin, and then we have the value for delta S in joule per Kelvin, and again we have the gas constant here. And solving for ln K, we get a value of negative 9.49. Okay, so ln K is going to be 9.49. Okay. And then we can plug it in, and this is now e to the minus x. Okay, remember, e to the minus x is going to be equal to k. And we plug the value of 9.49 into the value of x, and we end up with a small value for the equilibrium constant. Now remember, when we did this calculation in a previous video example, we found that the delta G value became positive, and of course the reaction was not spontaneous. Now this again makes sense because the K value is now small, indicating that this reaction is non-spontaneous.